All right, so today we'll finish up section 6.1 and then we'll be starting section 6.2, which will be our last section for this week. Okay, so yesterday we talked about angles and how we can measure them. And converting between radians and degrees is kind of like an algebra combining like terms. It's a very, very basic skill that you use for everything, okay, pretty much. So you really want to know how to convert radians to degrees, and especially memorizing the common angles, like the 30s, 60s, 45s. Those are good to just memorize. All right, so today we're going to talk first about arc length. So the idea of arc length is measuring the distance of part of the circumference of a circle. Technically, a circumference is an arc, but we normally don't call it an arc because it's so big it goes all the way around. And does anybody remember what that means if two things are proportional? Like, what does it mean if I said the amount of time you spend studying is proportional to the grade you get on the test? What would that mean? Yep.
They have a direct relation to each other. Right.
As one goes up, the other goes up. If you, and studying in tests isn't exactly, but this is a quick one I could think of. So, and it's directly proportional. That means if you were to double one of them, the other one would double. So, in a circle, if you draw an angle, let's say a 90-degree angle, it hits the circle there, and there's your arc length. Now, let's double the size of the angle. So instead of a 90, I'm going to make it a 180. So now my initial side, terminal side, hits here, hits here. That's my arc length. So by doubling the size of the angle from 90 to 180, I doubled the size of the intersected arc. Okay, so any question on that? It works the same way. If you made the angle half as big, if you made it like a 45, the arc would become half as big as a 90. Okay? So that's what it means to be directly proportional. And that's important because if they're directly proportional, we can set up a proportion to solve. Okay? And then use cross multiplying. All right, so we're going to start with that picture. So in here I have two angles. Because to set up a proportion, you need four things. Right? You have two fractions. You need a top and bottom on the left, top and bottom on the right. So here's going to be our four things. We have an angle, which I call theta 1. The rays of that come out, hit the circle right there. In between those 2 points, you get arc S1. Okay. On the other side, sharing the vertex, I have another ray that comes out, another ray that comes out, and those rays form the angle theta. And where it intercepts, where the rays of theta intercept the circle, I have 2 points. Connecting those points, I get arc S. So theta corresponds to S, theta 1 to S1. Now, in order to figure out the formula for arc length, we need a starting point. And I kind of mentioned this idea yesterday. We used an example of feet and inches. And what did we say? How many feet to an inch? What's the connection? Yep.
12 to 1.
Yeah, so 12 inches in 1 foot. Now, because you said the number 12 and you said the number 1, does that limit what numbers you could put on the other side to do the conversion between feet and inches? Like, can you only convert certain numbers from inches to feet or feet to inches? Because you gave me specific numbers here. So are there only certain numbers I could put here and here? No. Just because he used a 12 and a 1, that doesn't limit to what you can use on the other side. This is just a starting point that helps you to figure out what you want to know. So now you could put anything you want. 87 inches, x feet. But the key is you have to have something you already know to start with. Same thing here. We have to have something we already know from yesterday to start with. All right, so the starting point here is going to have to do with, let's see, S1 and theta 1. Okay. I could do it with S and theta, but I'm just going to use the S1 and the theta 1. Does anybody remember what we said yesterday about how big you would have to make this angle? And if you made what I just circled, that angle, what I'm thinking of, you would automatically know the size of this arc because it would be the same as something else in the circle. Remember that? How big does that angle have to be so that arc, S1, is automatically the same size as something else?
It has to be 1 radian.
It has to be 1 radian, yes. And if that angle is 1 radian, do you remember what that arc is the same length as in the circle?
The radius.
The radius, exactly. And that's your starting point. There's your 1 foot, 12 inches. And just because you might be like, well, wait, how can you just pick a specific number for the angle? Well, how can you just pick a specific number for inches? How can you pick 12? You can, because it's just it's a true statement. That's a true statement. If the angle is 1 radian, then the arc is equal to the radius. Okay, so now let's set up a proportion and solve it. So when I set up the proportion, I have to be consistent. Whatever I put on the top on the left, I have to put on the top on the right. Whatever's on the bottom on the left, I have to put the corresponding thing on the bottom on the right. Okay. So I'm going to put, let's do arcs in the top, angles in the bottom. So using the 4 things that I'm circling, anybody think they could set up a proportion with those 4 things that are circled? Don't worry about plugging into it yet. We're going to plug into it. But for now, just set up a proportion with the 4 things that are circled. Yep.
Theta 1 on the bottom.
Okay, yep.
And then S1 on the top.
All right, that looks good.
And then theta on the other bottom. And then S on the top.
Yeah. Basically, you can set it up any way you want as long as the diagonals stay the same. S has to be a diagonal from theta 1, and S1 has to be diagonal from theta. Okay. So you could flip it, different ways you can set it up. Now let's plug in our starting fact. Okay, the starting fact is going to go right there. So R over 1 equals S over theta. Just leave it because we don't know what they are. Okay, and now how do you solve a proportion? What's the technique you use so you can get rid of the fractions? Yeah. Cross multiply. And Megan, what's 1 times S? S. Actually, I have it right here. So S, and then on the other diagonal, S equals R times theta. So that's the arc length formula. S equals R theta. Okay, so S is the arc length, R is the radius, and theta is the angle, but we have to be careful about the units. Because if we go way back at the beginning, we assumed what I just underlined. We assumed that we were working in radians. That's how this whole formula was built. So when you use the arc length formula, you have to use radians. Okay. And in the formula, they can give you 3 types of questions. They can have you solve for S and give you the other 2 variables, R, give you the other 2, or theta, and they would give you the other 2. So they always give you 2 out of 3 variables. Which 2 depends on the question. Okay. Any questions on the arc length formula? Right, so that's the fastest way to probably find a length of an arc. There's other ways to do it too. Like, for example, if you had a circle and you knew the circumference of it, and let's say you put in like a 30-degree angle, you could figure out, well, 30 degrees is what percent of 360, and that tells you what percent of the circumference is included in that arc. Okay, so that's another way you could think about it. But rather than thinking about like it as a percent of a circumference, I would just use the arc length formula. Okay. So when they ask the question, there's a couple ways they can write it out as a sentence, or they can draw a picture. For most problems, I won't do both. For this one, I did. So I want to find the length of the arc. Okay. And you have a circle that has a radius of 2 inches. And the central angle is pi over 4. So here's a picture of what you're doing. You're finding the length of the red arc. Okay. Can somebody remind me what's my formula again for arc length? Leo?
S equals R
Theta. Okay, and we are finding the length, specifically length of the arc. So can you tell me what my radius is, Leo?
2.
Yep, radius is 2. And what about my angle?
Pi over 4.
Pi over 4. What would be the label on that? What's the measurement? Pi over 4.
That's radians.
Well, that's it. Yeah, it's pi over 4 radians.
Okay.
That's the units. You got to be careful whether you call that a unit or not, but we're not going to get into that. So we're using radians to measure the angle. So pi over 4 is radians what the formula wants us to be in. Then we're good. Okay, so just multiply straight across, and when you multiply and then reduce your fraction. Not as a decimal, just leave it as a multiple of pi. What do you get? Yep.
Pi over 2.
Yep, pi over 2. And what is that pi over 2 again? That represents the, what did we just solve for? Yep. Arc length. So, since it's arc length, what should I put on that? Yeah, Juliana? Inches, right? That is arc length. And there's 2 units in the arc length formula that are measured in length, arc length, and the radius. So it's pi over 2 inches, or if they wanted it as a decimal, pi over 2, just press your pi button, but this will be accurate enough for now. You divide by 2, and you get 1.57. Sometimes they'll ask you for a decimal. Sometimes they'll just say read your answer with pi. Questions on that one? All right, let's try this one. So this time they're asking for something different. Find the radius of the circle if the arc length is 3 pi feet and the central angle is 60 degrees. Okay, before I even start to think about doing calculations out, what's something right away that we need to fix? Yeah?
The angle is in degrees, not radians.
Right, so before we even plug anything into a formula, we should fix that 60 degrees. Can anybody tell me what 60 degrees would be in radians? Mm-hmm.
Pi over 3.
Yep, pi over 3. Now we're ready to plug in. So there's my formula. Let's just make sure we know which, where we plug in each number for the right letter. So Tanya, where does the 3 pi get plugged in?
The theta circle thing.
Well, what is the 3 pi?
No, it's what is that called?
The Greek letter?
Yeah.
That letter is theta. But what does the 3 pi represent?
Angle.
3 pi, this thing?
It's the arc length.
It's the arc length. All right, so the arc length is 3 pi, and what letter is arc length?
S.
S. Yep. So 3 pi. I know it could be a little tricky because there's a 3 in both of them, so if you're confused, like, wait, did he say pi over 3 or 3 pi? That usually doesn't happen, but in this one it did. So r, we don't know. And then pi over 3, we're plugging in for the radius, for the angle. Any questions on that? All right. So how do I get pi over 3 on the other side here? Got variable multiplied by a fraction. So how do we deal with that? Yep, what would you divide each side by?
Pi over 3.
Okay, you can divide each side by pi over 3, which is the same as multiplying each side by, the reciprocal. Either way you want to think about it. I usually think about it this way because then I don't have to think about fractions over fractions. 3's are gone, pi's are gone. And what do I get for my radius? Let's see, how about Jane? Do you see what I would get for my radius?
That would be
9. 9 what?
9 feet.
Feet, exactly. Radius is a measure of length. You have to go back in your problem and look at the units that you used for length. Feet. Okay, so that problem had a couple things in it. One, you were finding a different variable than the arc length. And 2, you had to change the angle to radians first. The only other variation on this problem would be if I gave you the S and the R and had you find theta. We did the other 2. Any questions on how you would do one like that? Now, if you had the S and the R and you solve it and you get an answer for theta, what's going to be the label on that automatically? What would this formula give you for angle, well, the way the angle is measured? Trevor? What would the units be on that?
For what?
The angle.
The angle?
Do you think?
It'd be like rad or
Yeah, it would be in radians, right? So if you had a question that gave you, let's say it was a multiple choice question, and all the choices were in degrees, well, this formula isn't going to give you the answer directly. This formula is going to give you the answer in radians, and then you would have to then take the last step to change it to degrees yourself, if they asked for that. Okay, they might not ask for that. They might just say leave it in radians. So any questions on that? Okay. All right, so that's the first thing we're going to look at. Second thing, kind of a separate idea, but definitely related to conversions, is angular velocity. So angular velocity is used to measure the speed of something spinning. I'd say a more common unit you might have heard of is RPMs. People heard of that, like revolutions per minute? Yeah. But in our book, the default unit, if they don't tell you a unit, is radians. Radians per whatever. Radians per second, radians per minute, radians per day. Doesn't matter. But if they ask you to find angular velocity, that's kind of the default unit. That's what they assume, and that's what they want you to use. If they want something other than the default, they'll tell you. Put your answer in degrees. Put your answer in revolutions instead. But the speed of something spinning on a circular path, that's called angular speed or angular velocity. We're not really going to differentiate between speed and velocity in this class. So I want to first just look at this disk I have up here with 3 different points on it and see why we need this. We already have a way to measure speed. You have like miles per hour or feet per second. Why do we need to measure the speed of something spinning differently than that? Does anybody already know? All right, can somebody give me the formula that you know for the time, the rate, and the distance? What's the basic distance formula involving those 3 variables? Yeah?
D equals RT.
Right, D equals RT. Okay, so keep that formula in mind. Keep that idea in mind as I explain something here. Okay. I'm going to take this disk and I'm going to revolve it 1 time. Okay, so maybe it took me about a second or maybe 2 seconds to revolve all those points 1 time. Okay. And I want you to focus, and I'll do it 1 more time, but focus on focus on the middle dot, this time. Right, now I'll do it again, but this time focus on another dot, maybe the red one or the outer black one. So what do you notice if you compare the 2 things I just said to compare, like the movement of the middle dot compared to one of the other 2? Yeah?
The middle one really doesn't move at all.
The middle one basically doesn't move at all. If it was exactly in the center, it wouldn't look like it does at all. So that has basically 0 distance. What about one of the other dots?
One of the further out ones moves a lot more.
Yeah, the one that's further out travels farther. Think of, revolving around like planets around the sun. The ones that are further out, they travel more distance in a revolution than like a planet closer, like Mars or Venus. Right? So the further you are from the center, the more distance you go. But let's look at the amount of time it took. So if you compare the amount of time it takes for all 3 of those dots to make 1 revolution, how does the time compare for this dot, or that one? The time for them to make 1 revolution. Yep.
Isn't it the same?
It's the same. They all made 1 revolution in exactly the same amount of time because they're all on the same disk. So they're all moving together. Well, that's a problem because now we have objects traveling different distances in the same amount of time. So what would that mean according to that formula? If you had an object that was traveling farther in the same amount of time as another object, what would that mean about it? Think about 2 cars. One travels farther in the same amount of time as another car. Well, what does that have to mean about it? Yeah.
Okay, some of them go faster.
It's going faster. So if you think of these as linear speed, these 3 points, the one on the outside is traveling the fastest. That one's kind of traveling middle speed, and then that one's traveling the slowest. And that's a problem. We don't want to have to describe the speed of these as 3 different speeds, depending where you are on the disk. So that's why we just use angular speed, and we can just say they all made 1 revolution in, say, 2 seconds. All of them have that exact same speed. So it gives us a way to describe the speed of something spinning, no matter where you are on the disk, as the same. Any question on that? Right. And what we're going to do is be converting some angular speeds into linear speeds. And the way you could think of that is pretend that this was a tire that was spinning, okay, like on a balancing machine. Maybe it's spinning 1,000 times a minute. And then all of a sudden that tire came off the machine, it hit the ground, didn't lose any traction, and just took off. Well, that would be instantly converting angular speed into a straight linear speed. Right? Same idea as if you were swinging an object on a rope. say you were swinging whatever on the end of a rope, and you were swinging it at like 60 revolutions a minute. So it was going around once a second. If all of a sudden you let that rope go, it's going to go in a straight line. Okay, whatever direction you let it go. That's instantly converting an angular speed to a straight linear speed. Right? So those are kind of situations you could think of for the math we're going to do, converting between the two. So as I already mentioned, angular speed is measured in radians per whatever time unit is in the problem. There's no default unit for angular speed for time. It could be seconds, minutes, hours, days. But the default unit is always you go to radians, unless they tell you otherwise. Okay, versus linear speed, that's the speed of something moving in a straight line. And some units you might have seen for that are feet per second, miles per hour, kilometers per hour, things like that. Now, some books come up with like some fancy formulas to convert between angular and linear speed, but I think the easiest way to do it is with dimensional analysis. It's exactly how I taught you to convert between degrees and radians. If you have units and you know it's in a fraction and you want to cancel one out, just make sure they're in opposite spots on the fraction. Some things that you do kind of have to know though, basic conversions. Okay. You have to know all the common time units. Seconds in a minute, minutes in an hour, hours in a day, days in a year, distances, inches in a foot, feet in a mile, those are the common ones. That's probably most of them. If there was anything like a really strange conversion, like you had to convert centimeters to inches, I would tell you how many centimeters in an inch. But common ones you should know. Okay, so as I just said, we're going to use dimensional analysis to do this. Has anybody done that before? We have, yeah, you just have a string of fractions and you just keep crossing out your units. Okay, I think it's easier to do it that way than to try to memorize special formulas for everything. Okay, so let's start off with a basic conversion just to practice dimensional analysis, which isn't even a rate, it's just a time. Okay, a rate is two things, it's a time and a distance. This is just a time, 3 days. So we're going to convert it 1 unit at a time. So what's the next unit down from a day, a little smaller, heading towards minutes?
24 hours.
Okay, so there's 24 hours in 1 day. So it's either going to be 24 over 1 or 1 over 24. Where does the days have to go? Top or bottom? Bottom. And now just fill it in. 1 day, well, day, 24 hours. And now days cancels. If you stopped here, you would have an answer in hours. Okay, what's the next unit down from an hour? Yep.
60 minutes.
So we have 60 minutes in 1 hour. And where would hours go? Top or bottom? Bottom. 60 minutes goes in the top. Hours goes in the bottom because it's in the top there, bottom there. It cancels out. And now just multiply straight across. You don't always end up with all ones in the denominator. Depends on the problem. All right, so we have 3 times 60 is 180 times 24 gives us 4,320 minutes. Bless you. Any questions on that? So that was just to kind of warm up and practice dimensional analysis. Now let's look at a rate. We want to convert 50 feet per second to miles per hour. What does that mean? You're traveling 50 feet in how many seconds? 1. 50 feet in 1 second. So now we have two problems. We have to change feet to miles and seconds to hours. They're totally separate, and you can do either one first. So let's do feet to miles first. Even if you don't know how many feet in a mile, you should know where feet is going to go in the fraction. Top or bottom? Yep. It's going to go in the bottom. So it cancels out. But now we need to know how many feet in 1 mile. Yep. 5,280. Yep, 5,280. Now if we stopped, we would have a speed in what units? Yep.
Miles per second.
We have miles per second. So the next step is to start to convert seconds up to hours. And you could just jump right from seconds to hours if you know how many seconds in an hour. Well, let's just do that. If you don't, go seconds to minutes and then minutes to hours. But how many seconds in 1 hour? Yep.
3,600.
Yeah, 3,600. Okay, so we did 2 conversions at once there by, we save a little time. And now if we multiply that out, we have a speed in miles per hour. Okay, so let's see what we get. So 50 times 3,600 divided by 5,280. So it's 34.1 miles per hour. You can write it as miles/hour, or you could put mph, either way. Okay. So 34.1 miles per hour. Any questions on that one? So that's a rate, but we're still using units that we're very used to. So now let's do some units we started learning about yesterday. Let's convert 200 radians per second to revolutions per minute. So that's 200 radians you're traveling in 1 second. Let's start with the unit that we're less familiar with, radians. Let's convert radians to revolutions. Yeah, Gracie, can you tell me how to set that up?
We said 360 radians on the bottom.
I agree, radians is in the bottom, and that means revolutions is in the top. And what did you say the conversion is between radians and revolutions?
I just don't know what it is.
360 would have to do with degrees in revolutions. So what's the conversion here? Yep.
Would it be 2 pi?
2 pi. I don't know where that goes.
2 pi radians.
2 pi radians in 1 revolution. Right, so that's the part that's less familiar. Now we just have to change seconds to minutes. Shauna, what would be the conversion that I would multiply by to get seconds to minutes here?
60 seconds.
1 minute. Right, now multiply that out. So you're going to have, let's see, 200 times 60. Well, that's going to be 200 times 6 would be 1,200 and add a 0, so 12,000 divided by 2 pi. Divided by 2. If I had a pi button, I would use it. That should be accurate enough. 1,909.9. Revolutions per minute. Question?
Yeah, when we use the pi button, you get 18,849.6.
18,000. Did I mess up my calculation? 200 times 6 is 1,200, right? 2 times 6 is 12. and then 12,000 divided by 2 pi. So 12,000 divided by 2 first, and then divided by pi. I think that's right. We needed 12,000 divided by, did you put it in parentheses?
Oh, okay. I forgot parentheses.
Yeah. Okay. And someone else can double check me if you want on that, but I think that's right. Okay. Any questions on that? So that's converting an angular speed to an angular speed. Now let's look at how we make the jump from an angular speed to a linear speed. So now in your head, think tire spinning on a machine, comes off the machine, hits the ground, doesn't lose any traction, and takes off straight. Okay, so we have a wheel spinning at, radius is 18 inches. It's rotating at 1,850 RPMs. Pay attention to whether they give you radius or diameter. Because if you start using formulas from geometry, depending on how you write the formula, you might have to change a diameter to a radius or a radius to a diameter. I'm going to skip part A. We just did that. So our wheel has a speed of 1850 RPMs, and they wanted us to change it to radians per second. We just did a conversion between RPMs and radians per second. We just did that. And part A wouldn't really help you to do part B anyway. So part B says find the linear speed of a point on the circumference of the wheel. Right? And the reason you do a point on the circumference is because think about the tire spinning on the machine. It comes off the machine and hits the ground. The part of the tire that makes contact with the ground is the circumference of the tire. Just to go back to this picture, if this was a tire, that part wouldn't be on the ground. That's in the middle of the tire. That point right there is the point that you're finding the speed of. So if you're thinking about it as linear speed, it's the fastest part of the wheel that's spinning. Okay, so let's start with our speed, 1,850 revolutions per minute. You should know that one. Like the RPM, doesn't stand for radians per minute. RPMs conventionally stands for revolutions per minute. Revolutions, 1 minute. Okay, so it says find the linear speed, and it wants it in feet per second. Well, let's deal with the time first. How many seconds in a minute? 60. Right. So now we have a speed in revolutions per second. Now we want to change revolutions to feet. Even if we don't know the conversion yet, where would revolutions go? Yep. Would go on the bottom. Feet would go on the top. Now, this is the kind of conversion that's a little different. There's always 60 seconds in a minute. There's always 60 minutes in an hour. There's always 24 hours in a day. Those kind of conversions, they never change. But the number of feet in a revolution, is that a conversion that's always the same? No, it depends on what you're revolving around. Are you traveling around your house? Are you making a revolution around that? Or are you talking about the Earth revolving around the sun one revolution? Okay, the number of feet in a revolution changes. So that's what we need to figure out. And now we're going to use some of the information they gave us about the size of the tire. So here's our tire. It's 18 inches. How can I figure out how many feet in one revolution? What's another name for one revolution? It's the what?
The circumference.
It's the circumference. So basically, I want to figure out if this was like a steel wire and you cut it and then laid it out flat, how long is it? That's what I want to find out, and the circumference formula will do that. Leo, can you remind me what that is?
is it? It's not 2 pi r.
Yep, so 2 pi 18. So my circumference is 36 pi inches. Feet. Oh, wait a minute. No, that's inches. That's fine. But if we're going to do it that way, then I need to adjust this. That's how many inches in a revolution. That's not how many feet. But you could easily convert that to feet, but we'll do it as 2 steps. Right, so 36 pi inches in a revolution. And then what's the conversion between inches and feet? 12 inches, 1 foot. And revolutions. So we look at your units in the top, you have feet, in the bottom, seconds. Okay, now just multiply straight across. 1850 times 36 times, if you use that many decimals for pi, you're good. Times pi, divided by 60 times 12. So divided by 60, divided by 12. Double check me on that, but I think it's 290.6 feet per second. 290. Okay, did anybody else get 290.6 that checked it? These are kind of problems that it's hard to just say, well, that seems reasonable, because there's so many conversions. I have no idea if that's reasonable. But that's what someone, you got that? Okay. So any questions on the concept of angular velocity? Okay, so we started with looking at arc length. Okay, we did that. Then we went to angular velocity. And the last thing we're going to look at starts our last section for the week. Okay, so these are 3 kind of totally separate things. Okay, has anybody done unit circle trigonometry before? So in this section, this will be the first time that in this class I formally define the sine, the cosine, the tangent, the secant, the cosecant, and the cotangent. If you've done SOHCAHTOA, that's right triangle trigonometry. This is different. This is unit circle trigonometry. Both of these get at kind of the same thing. One thing that students have mentioned that have gone on to calculus is when you take calculus with Mr. Babb, he expects that you know this. Like, for example, if you ask somebody the sine of 60 or the sine of 30, this gives you a way to do it in your head very quickly. In fact, so quickly, if you do it enough, you memorize it. And going into calculus, you really need to know the 6 trig functions that I said, sine, cosine, tangent, secant, cosecant, cotangent. You need to know all of those for angles that are multiples of 30 and 45. So like sine of 120. Even if you didn't have it memorized, you should be able to figure it out in probably under 5 or 6 seconds. Think about it in your head, visualize a picture, and get the answer. Right? And that's what this is going to help you to do. Angles that are not multiples of 30 and 45, you wouldn't be expected to know that. Like, you'd never be asked off the top of your head, what's the sine of 57.6? Nobody knows that. But angles that are multiples of 30 and 45, that's what we'll focus on. All right, so in unit circle trigonometry, we're going to start out with a circle. And on that circle, you can label the radius as 1. Okay? Because in a unit circle, the radius is always 1. Now, what I'm going to do on that circle is draw an angle in standard position. Like that. If you draw an angle in standard position, the terminal side is going to hit the circumference of the circle somewhere. Okay. Where does it hit it? Right here. that point that I just labeled, where the terminal side and the circumference intersect, that point has coordinates. It has an x coordinate, it has a y, it has an x part to the coordinate and a y part. The whole goal of unit circle trig is to figure out that coordinate. If you can figure out that coordinate, you can do what you need to do. Now we'll talk about how to do that. But any questions on the goal? Okay, so goal, figure out that coordinate. Very easy to figure out if you're on an axis. And let's look at those coordinates right now. I'll just draw, I'll erase this and just draw right on it again. So if the radius is 1, this is the origin, that's 0, 0. What would be the coordinates of that point right there? If you've gone from the origin 1 unit away from it in a horizontal direction. Yep.
0,
0, 1 would be up here. 1, 0. Okay, so coordinates for 0 degrees, going right 1 is 1, 0. The coordinate for 90 degrees is 0, 1. How about the coordinate for 180? Yeah.
Oh,
Negative 1, 0. And how about the coordinate that would represent the terminal side of the angle at 270?
0, negative 1.
0, negative 1. Those never change. In fact, all the coordinates I'm going to teach you on a unit circle never change. There's a total of 16 coordinates we're going to learn on this circle. There's 4 of them. There's 3 more in each quadrant. And you might think, well, geez, how am I going to remember 12 more? Well, you really only have to remember 3 more. If you can remember those 4 and 3 more, then you can figure out any angle that's a multiple of 30 and 45 due to symmetry. Okay? If you have a 45-degree angle here and you know the coordinates, I'm not going to label it. Let's say they were x, y. Well, the coordinates here would be negative x, y. It's just a mirror image. Same thing if you were down here. All you have to know is the x and the y for all of those. You're just throwing a negative in front of it, or sometimes in front of both parts. And there's 3 we're going to do like that. This one, and this one. So there'll be 3 coordinates you have to know in quadrant 1, and then you can mirror image them into any other quadrant, and that will give you all 16 points. I'm not sure we're going to get to all 16 today. I don't think so. Yeah, I know we're not. We're going to stick pretty much just in the first quadrant. I don't even know if we're going to get to these 3 today. Probably tomorrow. Okay, but for today, you should definitely know all the coordinates that are on the axes. All right, so this part, you don't have to worry about this. I told you that for angles that are multiples of 30 and 45, the whole idea is to find the coordinate. Okay, so if you want to copy something down, the part I would copy would be this. So these x and y values, and by these I mean the coordinates. Coordinate for point. And what's the point? It's where the terminal side and the circumference intersect. So if you need to write that, you can. So find the coordinates, and those x and y values will allow you to find the sine, the cosine, the tangent, the secant, the cosecant, and the cotangent of your angle. So that's great if they say to you, what's the cosine of 90 degrees? But knowing the angle isn't really helpful. You have to figure out, okay, they want the cosine of 90 degrees. Step one is to figure out the coordinate for 90 degrees. If you can't get the coordinate, you can't do unit circle trig. And then what do you do with the coordinate? Well, there's a formula you plug it into. There's 6 different formulas, depending on which trig function you want to know. Sine, cosine, tangent. Secant, cosecant, or cotangent. So the 3 trig functions on the left, those are the ones that are the most basic. And if you look at any scientific calculator, those are the ones you have buttons for. Sine, cosine, tangent. The other 3 that I'm going to mention in a minute are used less often. They're still used, but just not as much. 6 trigonometric functions. Below them, I put the abbreviation. All trig functions can be abbreviated with 3 letters. It's usually the first 3 letters of the full function name, but when we get to cosecant, that's spelled C-O-S-E-C-A-N-T. Well, the first 3 letters of that already are used for something else. So I'll show you how they abbreviate that one. Okay. So if you have a problem and they ask you for the sine of something, all you really need from the coordinate is the y value. The y value of the coordinate is the sine. The x value of the coordinate is the cosine. And then for the tangent, you need both. You take the y value of the coordinate, divide by the x value of the coordinate. Okay, so those are the other 3 trig functions. Cosecant, secant, and cotangent. Secant and cotangent, abbreviated just like you would expect, but can't use COS for cosecant. So they do it by the syllables. Cosecant. And the nice thing about the 3 on the right is if you know the formulas on the left, you automatically know the ones on the right. Because the ones on the right are the reciprocal functions. Okay, what does reciprocal mean? Simpler word. Yeah. Careful. Opposite usually means to put a negative in. So opposite means put a negative, but reciprocal means, flip. So if you're like, well, wait, how do you flip that answer? Well, think of it as y over 1. I wouldn't normally write that, but I will for this one. So if I lined up the reciprocals right across from each other, what do you think the formula for cosecant is? Yeah? Yeah. So it's just the sine flipped. So if you know the sine value, say was 0.6, the cosecant would be 1 over 0.6. Flip it. How about the secant? Yep.
1 over x.
1 over x. And then the cotangent, x over y. So if you can just remember the first 3, you don't have to remember the other 3. Just remember, oh yeah, flip it. Flip it. That's all you got to do. And if you're familiar with opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent, this is exactly the same thing. It really is. If you think of this, people that know sine as opposite over hypotenuse, if you're like, well, how is the 1 a hypotenuse? Imagine making a triangle in this circle. There's your hypotenuse, but it's also the radius. And we're in a circle that's a unit circle. The radius is 1. So that 1 is really a hypotenuse. Okay, but we don't get into calling it that until we do right triangle trig. Special name for those 4 angles that I gave you before, they're called quadrantal angles. It's not super important to know that, but it's a term that could come up. And they're just because they divide the quadrants. They're on the axes. Okay, so how do we actually do a unit circle trig problem? Okay, there's 2 steps. Step 1, find the coordinate. That's step 1, find the coordinate. Now, sometimes they will give it to you. They'll just say, here's a coordinate, don't worry about finding it. That would be a problem. I'll come right back to this. But that would be a problem like this. Here's a coordinate. You don't have to worry about finding it. If they give you the coordinate, you can jump right to step 2. Now, up till now, I've only shown you how to find 4 coordinates. And those are the coordinates for the quadrantal angles. So in the homework tonight, I can't ask you about anything other than 0, 90, 180, or 270. If I want to ask you about something other than one of those 4, I'm going to have to give you the coordinate of it. So this coordinate represents some angle, but it's definitely not 0, 90, 180, or 270 because look at the numbers. It's a 1/2 and a square root of 3 over 2. I didn't use those 2 numbers anywhere in the 0, 90, 180, or 270. So it represents something, but it's not important what it represents. All you need is its coordinate. We'll talk about what it represents tomorrow. Okay, so step 1, find the coordinate if it's not given. Step 2, plug the coordinate into one of the 6 formulas from the other page. On a test problem, I would not ask you to do all 6 trig functions in the same problem. I would ask you for 1. But we'll practice doing all 6 so you know how to do them all. Okay. Let's start with 0, 1. Step 1, find the coordinate. We already have it. It's right there, 0, 1. Now, plug that coordinate into the 6 formulas we just had on the other page. What was the definition of sine? Sine equaled, yep, y. And what's y in this case? 1. So whatever angle this represents, which you should know, but you don't have to say it because it's not asking, but whatever angle that represents, that's the sine of the angle. Now I'm asking, what does that angle represent? What coordinate is that? Yep.
90 degrees.
That's the coordinate for 90 degrees. So on your calculator, if you typed in sine of 90, you would get that as an answer. Okay. Now we're doing the cosine of it. Okay. Cosine is equal to
0 for
x, which in this case is 0. And the tangent. See if you can do that one. Okay, tangent, y divided by x. Well, this is y, this is x. So just imagine putting a fraction bar right there, and that's your answer. Yeah. Undefined, yes. Now, to find the next 3, all you have to do is take the 3 that you just had and do what with them? Do what?
Do the opposite of
Okay, well, opposite would mean like we put a negative in
the
front.
flip
Flip it.
opposite.
Yep. So flip it. What's the reciprocal of sine? What's the name of the function? Cosecant. Cosecant. And what's the reciprocal of 1? 1. There's 2 numbers in math you can flip that stay the same. 1 and negative 1. What's the name of the reciprocal function for cosine? The secant. And now, if you're wondering, well, how would you flip it? Make it a fraction. It's 0 over 1. What do you get if you flip 0 over 1? Yeah?
1.
If you flip 0 over 1, it becomes 1 over 0, which is, Trevor?
Undefined.
Undefined.
Oh.
If you flip 0, you get undefined. If you flip undefined, well, we're about to talk about that. What's the name of the trig function that's the reciprocal for tangent? Cotangent? And if you're like, well, wait, what fraction did we have? I just wrote it underneath. It was 1 over 0. So if you flip it, you get that, but you got to tell me what that is. That's 0. Remember, a number divided by 0 spells no, so you can't do it. Number over 0? No, you can't do it. Any question on that one? This one, I'm going to skip over, but I think you should be able to do it. I'm giving you the coordinate again. The only thing is, what's the rule with square roots? What do you have to make sure of when you have fractions with square roots? What can't you do? You can't have it in the bottom. So when you do some flipping, you are going to end up with a square root in the bottom, and you need to fix that. That's from Algebra 2, Algebra 1. Let's look at this one. There's a bunch of them. They're all, doesn't matter which one we do. The point here is they're asking for the 6 trig functions of 90. What would you have to do first in this problem? Yeah. You'd have to get the coordinate. And what's the coordinate for 90 on a unit circle? 1, 0 would be the coordinate for 0 degrees.
Oh, 0.
90 is up.
0.
Yeah, 0, 1. Well, if the coordinate is 0, 1, we just did that. So the only, I'm just going to say C, example 1. The only extra step here was you had to find the coordinate first, but we just went through everything. What about 270? What would be the coordinate there? Yeah?
0, -1.
0, -1. Well, if you can do 0, 1, you can do 0, -1. It's just change the 1 to a negative. And you do the same thing. How about pi? What would be the coordinates of pi? Yeah?
Isn't it -1, 0?
Yeah. What is that in degrees?
180.
It's 180. So it's 180 degrees. So if you need to, change it in your head. And then think, okay, 180 is left, 1 unit. -1, 0 would be the coordinate to go left 1. And then you would plug in all the numbers just like usual. Any questions on how you'd plug them in? With quadrantal angles, you don't get a lot of variety in the answers. You get 1s, 0s, -1s, or undefined for every one of those answers. You can't get anything else. This would be another one that you might want to change to degrees first. Let's do it using kind of a trick. What's pi over 2 in degrees? Yeah? 90. So this is really 90 times 7. What's 90 times 7? Yeah? 630. Now that's an angle that's too big. We talked about how to make it smaller. How can you make an angle that's bigger, smaller? Or the fancy way is, give me an angle that's coterminal with that, but I want it less than 360. Subtract 360. So 630 minus 360. It's a 270 degree angle, and we just talked about that one. You find the coordinate, then plug everything in. Same thing here. What would be an angle that's coterminal with -90? Yeah?
270.
270. So this problem is exactly the same as the last problem. It's the same angle, same answers. You just have to find the coordinate, which we did a few problems back, and then plug it in. Right. right, so for 6.1, on 324, I'd like you to try 56 to 61 and 70 to 73. And then on 335, there's a couple things, so read the directions carefully for that. I'd like you to do 158 in the book and do exactly what they ask you to do. And I'm adding a couple extra questions. Find the 6 trig functions of 158 in the book. And these 3 other problems that I added. Okay, so for 1, 5, and 8, 3 pi over 2, 2 pi, and then the coordinate at the end, you should have 6 answers per problem. So sine, cosine, tangent, secant, cosecant, cotangent. All 6 of those things for everything I just underlined. It seems like kind of a lot. You're like, wow, it's 36 different answers for that last part, but really, the answers should come very quickly. All right, so we'll take a look at that tomorrow. We'll finish up 6.2, and then on Thursday, we will have our test. And we'll finish the test on Friday.